Day 1 of chapter 5. Chapter 5 getting into what are called continuous distributions. Continuous probability density functions, to be like purely mathematical here. So when I say, so before we had PDF, which is a probability density function or a discrete one, these probability density functions are continuous. So we're going to call them typically, instead of just, so again, before we had discrete, and for discrete we called them PDF. For continuous we call them, that should have been a C, CDF. So when we're talking about a continuous density function, we're going to use CDF. When I talk about a discrete probability density function, I'll say PDF. And that's fairly consistent in most of the stats types classes you might see. They'll call it a PDF for discrete, CDF for continuous. But as always, check with professors in the future. If you take another stats, go on to something in the master's degree and you got to do a stats class, they might just pick a different, slight way of saying it. That's just what you'll have to deal with. All right, so in a discrete, remember a discrete, that's what we've done up until now. A discrete is when there are a finite set of outcomes, and then we count how many times those finite set of outcomes happen. So we did things like the sum of two dice. You roll two dice, sort of the sum of two dice, that's finite. You can get a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. The sum of two dice is a finite set of outcomes. It's discrete. We looked at cards. You get a queen or a face card or red cards, diamonds. We've done some of those things. Those are discrete things because there's a finite set we can see. Okay, and then within each one, we say how many times did that happen? And then we created probability density functions, right? Remember we did the one for sum of two dice. So the sum of two dice. So that was 7, 8, 9, 10, 11, 12. And if we had this bar, that bar's height, if you remember when we did it in class, was 6 out of 36. Sorry, it's 7. 7 out of 36. This one was 6 out of 36. That's 5, 4, 3. No, I was right the first time. That's 6. 6, 5, 4, 3, 2, 1. Because there's only one way to get a 12. So that, in this case, when we're drawing these, this is a bar graph, not a histogram. It's a bar graph. A bar graph because these are qualitative values. And you might say, but it's not. It's quantitative. It's a number, true, but it's a quality. We're saying, what's the sum of the dice? The sum of the dice is 7. Remember, quantitative versus qualitative. Quantitative is something we can measure. All right? When we add up two dice, we're taking the sum of it. That's not something we're measuring. We're just counting the number of dots on that dice and then adding it up to the other dots on that dice. It's a quality, so it's a bar graph. Remember, bar graphs do not overlap. There's no overlap. Histograms do. When we get to continuous, then we'll be doing histograms. We've already done histograms and box plots. When we do continuous, and now in continuous, it can be either actually continuous, that is, there's an infinite number of possibilities, or it can be what we just call it's essentially continuous. When you're counting how many minutes does an individual student study in a given week, is that actually continuous? No, there's not an infinite number of minutes that exist in a given week. But for most time, when we're talking about time in general, we're typically going to talk about that as a continuous variable. We're measuring time in seconds or minutes or something like that. Again, you're probably not, for those of you that were like chess players, you're not like punching the clock, like on, off, start, stop. So we don't have it to the nearest second or things like that. But time itself is continuous. So even though it might not be actually continuous, number of minutes in a week, we'll consider it to be essentially continuous for what we're doing there. So discrete, continuous. This one back here. If we added up all of these probabilities, do you remember what they all added up to? 1. All the probabilities add to 1 because they account for every possible outcome. You'll get one of those outcomes no matter what you do. You roll two dice, you're going to get one of those outcomes. you look at the probability of all of them happening, overall, we're going to end up with a probability sum total of 1 for continuous, or for discrete. And the same thing will hold for continuous. As I hear everybody else's phones dinging, I'm going to turn mine off. There we go. To here, if I would have said 4 to something, we would have looked at each of the bars. Like if I wanted to find the probability from 7 to 9, that means it's going to be a 7 or an 8 or a 9, or means add for my probability rules. So I'd add those 3 probabilities up. Within the continuous, we have what's called, the first one, it's the most basic, call it the quote-unquote easiest one to start with. It's a uniform, continuous probability density function. Lots of words. So a uniform one means that the function itself, as you look at that graph, is the same on the entire interval. And this interval goes from 0 to 20. So from 0 to 20, I would write this. We've been getting in the habit of doing this, I hope. X follows a uniform distribution. And the uniform distribution, now with the other ones that we've done, like for a binomial, remember it was NP. For a hypergeometric, that was the bigger one. It had like the number that's the subject of interest, comma, the number of the other people, comma, then how many are in my sample. In a Poisson, it was X is approximated by P, and then in parentheses, all we had was the mu, or the lambda, depending on if it was a beginning or extended version. For this one, it's the lower bound, comma, the upper bound. From 0 to 20. And when you look at a uniform, just like in, same thing goes here. But now, it's not an individual value, it's a range of values. The range from 4 to 15. So the way we would write that would be, again, looking to make sure that my variable is x, which it is, so I'm just using proper notation. Probability, and I'll have x is less than, x is greater than 4, x is less than 15. And some of you might say, shouldn't it be this? And I'll explain in a second that it doesn't matter. Just going to erase it for now. So that notation is for that area. So you're going to pause here for a second. You're going to turn and talk with your people that you're sitting next to, and you're going to say to one another, what is the area of that rectangle? Go. So again, what we're looking for is we're looking for the probability that x is between 4 and 15. And if we remember here, we don't have an individual value, but we have this value that's an area. The area under the curve is grand total. So the total area in that curve is 1, just like it was for our discrete. So the total area in that rectangle has to be 1, represented basically 100%. 100%. So if I said from 0 to 20, what's the likelihood I'm in that interval? Well, if that's my whole function, it's a 100% chance that I'm between 0 and 20 because that's my whole interval. Here I'm looking at just from 4 to 15, so we're just finding just the area of that one rectangle. So I look at that rectangle, and that rectangle has a base length of 11, and the height is 1/20. Now, either they give that to you, which they did here, but this would fall into the category of me going, you should know how to find that. How do we do that? If I have a rectangle that's length is 20, what's the height so that the area is 1? Well, if the base length is 20, the height has to be 1/20, because 20 times 1/20 is 1. If my base length is 10, the height would be 1/10. If my base length is pi, the height would be 1 over pi. But in this case, it's 1/20. So this probability of that area will be the area of that rectangle. The area of that rectangle is 11 times 1/20, so 11/20. Ta-da. And we just leave my answer just like that. The only time I would ask you to change it is if I ask you to find it to a nearest percent. We'll then change it to a percent. just over 50% chance that whatever this uniform distribution is, that if I randomly select a point somewhere between 1 and 20, there is an 11 out of 20 chance I'm between 4 and 15. So here's what you're going to do with your partner here for a couple of seconds, or minutes, I should say, more than a couple seconds. Suppose the time it takes a 9-year-old to eat a donut. So I made up these numbers. We all know 9-year-olds do not take 4 minutes to eat a donut, right? But let's just say, because I need to create something here, that it takes a 9-year-old sometime between a half a minute and 4 minutes to eat a donut. And it's an equally likely chance it happens anywhere in that time zone. So that basically means this will be a uniform distribution. So let x equal the time in minutes it takes a 9-year-old to eat a donut. First, decide how you're going to write u. X follows uniform distribution with those two numbers. Then find those next three things with your group. Talk amongst yourselves. Take guesses if you don't know. And we'll come back together and find solutions. All right, turn and talk. So again, uniform 0.5 to 4. The correct answer is 2 minutes and 25 seconds. It's the average of the upper and lower bound. In a uniform distribution, the nice part is if I were to draw this, so here's my graph. That's 0.5. That's 4. The average will happen in the middle, right there, and it's the average of the upper bound and the lower bound. So that's the mean. All right. So then we need to say, okay, what is the probability that a randomly selected 9-year-old takes more than 2 minutes? I'm going to tell you this now. I will repeat myself probably many times, and then on the exam, if you don't do it, I usually look at that and I would say in my head, they didn't do what I told them they had to do on every type of a probability problem, which is draw a picture. All these scenarios that we're going to have, whether it be a uniform, an exponential, a normal, eventually chi-squared, f, all the different distributions have very specific shapes. And when you do it, you draw a picture, label your boundary points, shade the area that you're looking for, and then do calculations. And the reason why we do it is because sometimes you'll make a picture, you'll do the thing, you'll shade it all up, and in that you can visually see about what your answer should be. And then when we get to some more of our sophisticated probability distributions that we're going to work with, our density functions, we're going to use different tables of values to discern what areas are, because you're not required to have calculus to be in here. If this were calc-based, we'd actually then go and we'd do the first derivative. We do the integral of each of the equations, and they're exhausting equations, which is why we don't do it this way. But if you did, you'd find the integral of the certain areas, you'd find those areas, then you'd say, ta-da, this is what it is. But for us, we're just going to look at tables of values. But in this case, we don't need a table of values because it's a rectangle. So the first thing you're going to do, if you didn't do it already, you're going to label the boundary points. And the boundary points would be where and where. Hold on. 3's. What's the lower boundary point? Where are my 3's? What's the lower boundary point of the shaded area in my rectangle? Of what? So the second question asks, what is the probability that it takes more than 2 minutes for a 9-year-old to eat a donut? My lower limit will be 2. Because that I want to know that. And then it says 2 minutes or more. So my upper limit is 4. Because it takes a 9-year-old anywhere from a half a minute to 4 minutes to eat a donut. And then I shade the area of my desired location. If I've drawn it to somewhat scale, I can look at this and I already know it will be over 50%. How do I know it's over 50%? Well, that's because that was the mean. That was my mean right there. The mean. We said was 2 minutes and 20. Now, is it 2 minutes and 25 seconds or is it 2.25? 2.25. All right, so that's not, all right, because a quarter of a second or a quarter of a minute is 15 seconds. But anyways, so just making sure we're using correct units. So 2.25 was the mean. So now the probability is finding that area. And lucky for us, it's a rectangle. And you can find that area, and someone in the twos will give me that area. And then everybody else will be ready to either confirm it or refute it. So, I'm going to write correct probability notation. This is x. I forgot to label my graph. Probability x is greater than 2. All right, someone in the twos. Where are my twos? There's a couple twos.
4/7 or 3/5.
So yes, starting by going, what's the height? The original full rectangle had a full length of the bottom of that rectangle of 3.5. So that meant the height was 1/3.5. Then I can use that in the green area to say, well, it's too long and 1/3.5, and I'll go like this. And if you did this, I'm giving you, that's full credit for me. It doesn't have to be like this. All right. If you had me back in intermediate algebra, you know what I tell you to do. You'd have to change it to here. But we're not there anymore. We've now advanced past that. And again, if we get to different classes, different other professors and some other chemistry or physics, they're going to have their own rules. You just got to go with, why do they all change? Because that's life. We're just teaching you to be adaptable, if nothing else. Why can't there just be one system of doing everything? Because we're America, right? No, I'm kidding. All right, so last one. If you haven't figured it out yet, go ahead and do that now. I'm going to hit pause. Now that we've covered these two, maybe it inspired you to go, oh, I think I know what we're doing. So go do that last one now. So again, if you show the work, and it's a wrong value, but I can see where you got the numbers from. So maybe you wrote something down, and some of you are sloppy writers. I am. You've seen it, my work. All right. And if I lose track of what a number is, but I show convincingly that I'm following the right steps, you'll get full credit. If you look at this and you're like, well, I did the work in my head, and you write down a percent, even if it's the right percent and you have no supporting work, you will not get credit on an exam question. If you have the full supporting work, that's how you have to get there. If you have supporting work and you make a clerical mistake and you still get a wrong answer, you'll still get full credit if you're doing all the right steps. All right, because I'm not testing you on your ability to read your own writing. You're going to have to figure that out eventually to keep a job. But for your own sake and my own sake, as long as you're following steps, you're like, oh, yep, they did the right thing. I see where they messed up a number here. That doesn't bother me because so much of statistics is process. Answers are just, that's it. That's just an answer. But the process tells me that you're thinking through, following the procedures, doing certain things, and getting yourself into a place where you can generate an answer that would make sense. All right? But you saying, well, I did it in my head or I did it in my calculator. One, I don't have access to your calculator. I don't want it. Two, I can't read your mind. Thank you, Jesus. I never want to. So what you have to do is you have to show me the work. All right? So again, either you didn't do it or you guessed, which is hard to do. And then the third option, which I never want to say out loud, but, people cheat. I don't care. That doesn't help me at all. Following processes. Now, if you follow, this is the best ever. Back in my high school days when two students would turn in identical work that was wrong, they made the exact same clerical mistakes that were exactly wrong. And they're like, and then I'm, bring them in, and they both adamantly convinced themselves that they did not cheat off of each other until they realized that, yeah, but you showed the exact wrong mistake at the exact same time. How could you have copied down your number wrong? Yeah, anyways, so I digress. So when we do this one, the probability that a different 9-year-old, so we're going to start with a new picture because I have a different 9-year-old. There's my picture. Here's my rectangle from 0.5 to 4. And then it says, what is the probability that a different 9-year-old child eats a donut in more than 2 minutes? All right, so I got a 2-minute mark again, right there, 2. More than 2 minutes. And is all the way more? Yep, so this is shaded. Given, this changes everything. So instead of out of all of it, it's not out of all of it anymore. It's given that they had already been eating the donut for 1.5 minutes. So this right there, 1.5 is my starting point. And this area over here, we pretend it doesn't exist. So what I have now is I now have this full rectangle. That's my full rectangle now. That yellow rectangle is my full rectangle. I've eliminated this. It no longer exists. If it helps, I'll do this. Given 1.5. Just like when we did the probability rules, once you say given, we've redecided the denominator. The denominator is no longer the old one, it's the new thing. In this case, my denominator is my overall area out of 1. Well, I have to redefine my 1. My 1 goes from 1.5 to 4. So what is this length? From 1.5 to 4? 2.5. So if I need to, I'm just going to make this a little. This is x. This is 2.5 in length. What's my height of my rectangle? 1 over 2.5, because it has to multiply to 1. My new probability is from 2 on up. So how I would write this is the probability that x is greater than 2, given x is greater than 1.5. That's how I would write it in notation from what the original sentence was. But then I can go to my rectangles and say, oh, I just redefined it. Instead of going from 0.5 to 4, it goes from 1.5 to 4, which means my height is now different. And then I can find the area of my green rectangle as from 2 to 4 is 2 over 2.5. Base times height. My green rectangle, the base was from 2 to 4, so that's 2. My height now changed to 1 over 2.5. And again, there might be some of you that say, I really need to change that to 4/5, and you certainly can. That is fine. All right. But showing me the 2 over 2.5 is all I would need. If I were to go back, this is a quick little refresher. Probability of A given B. That's a parenthesis. Remember, we did these two probability formulas a while back. Probability of A union B, probability of A intersection B. And one of them included that. And I showed you that you could rewrite it if you wanted to as probability of A and B divided by the probability of B. So how mine would be redone would be the probability that x is greater than or equal to 2, or greater than 2, and greater than 1.5, divided by the probability that x is greater than 1.5. That's going to be harder to do. But visually, a little bit easier. Just using a little bit of geometry. And so now, I said I would get to this one little nugget, which I'll share it with you now. Let's move, come on. Will everything move up? There we go. We'll move that up. If I go back to my original drawing, 0.5 to 4. And I say, what's the probability that x equals 2? You would look at that picture and say, all right, the process and procedure is I need to mark my boundary points. Where's my boundary point? Right there. I'm going to go up. And then I shade the area. And then I need to find the area of the rectangle at x equals 2. The height of this, once again, was 1 over 3.5. All right. What's the width of that? 0. Lines don't have widths. So 0 divided by any number is always 0. So in a continuous probability density function, the probability that any single answer happens is 0. The other way to think about it, how many ways can 2 happen? Once. How many possible outcomes are there? How many numbers exist between 0.5 and 4? There are an infinite number of numbers between between 0.5 and 4. Since there's an infinite number, 1 over infinity approaches 0. So either if you want to think about it mathematically in terms of numerics, or you think about it geometrically, the area of a line is 0. A line only has one dimension, so it cannot have area. Area is two-dimensional. What we're going to do is take a quick look at some information and use this as a way to review a little bit, but also talk about exam questions, and I can share my approach and my philosophy to how I grade. But so to make it relevant, I grabbed the weights of the 2023 Kansas City Chiefs. There they are. So you can go online and look at it. Don't do it right now. But, anyways, probably not the kicker. Kickers these days all are like these beefier guys, and yeah. All right, so anyways, first question for you to consider with your group and who you're sitting next to, and I'll call out a card here in just a moment, is that question on the right, which is which type of summary statistical display would be appropriate and which would not? So we've talked about lots of different types of graphs, basically. Statistical summary displays. All right, what would be an appropriate type of way to graph that data? What would not, and why? Take a few seconds and talk with your partners. So number nines, give me a plot that would be appropriate for this type of data. Where are my nines? All right, nines, what is one type of a display that would be appropriate for this kind of data? A histogram. Why was a histogram be appropriate?
Good for large sets of data.
A histogram can work for large sets of data, true, and, say again? This would be effectively or essentially continuous data, which means it's what type of data? Starts with a Q, but they both do. It's quantitative data. It's measurable. You can measure someone's weight. So measurable data, a histogram, is an effective tool to display statistical values or statistical data because it's a large data set as well. All right. Number 8s. Where are my 8s? Give me a graph or a display that would not be a good choice. What would be a type of graph that would not be a good choice, or essentially you can't do it with this type of data? Doesn't matter what we're trying to show. What type of a data is a pie chart good for? Well, percentages would be what we display in it, but what type of data would be displayed in it? You would say percent of this and percent of that, but what type of data? Categorical data is best displayed in a pie chart. This is not categorical data. Bigger, fancier word, qualitative. It's not qualitative data. It's not a quality. These are quantities. These are measurable outcomes. So a pie chart would not be good. So bad, in the bad category, would be pie chart. All right. I keep getting repeats. 4s. Where's my 4s? Here you are? No, 3s. Where's my 4s? Someone over here is a 4. All right, we'll go with 3s since they're the most vocal ones about not being 4s. All right, 3s. What is another type of a statistical display that you could use and why?
Box plot.
Box plot, tell me why.
Large amount of data displayed very easily. It's easy.
Large data set, yes.
Yeah.
And?
If you know what you're looking at in a box plot, it's easy to read
Yeah, a box plot, you can pull out information quickly, like the median, the quartiles, minimum, maximum, for sure. Yep. But the biggest reason why we can use a box plot is what type of data? It's quantitative. Quantitative data, histograms, box plots. Qualitative data, categorical data, pie charts, bar charts, Pareto charts. I know I heard some murmuring at some point where people were talking about a scatter plot. Scatter plots if you have paired data for an X and a Y plot. We don't have paired data. If we had their heights to go along with their weights, then, yes, we would plot that. Each individual person's height and weight would be their X and Y coordinate. We can plot that and then look at trends. Typically, taller people tend to weigh more. Okay, but there's outliers, of course. But you look back here. So here we go. I took on the left for you, that's, what do we have over there? The Chiefs. On the right are the Niners. Oh, look at this. So this is the 2023 weight distribution as is recorded online for the weights of the Chiefs on the left, the Niners on the right. An exam question would be this. I would give you this and I would say, actually I wouldn't say plots, I would say compare the Chiefs and the Niners. And I would leave it very vague because there is a lot to cover. This would be a lengthy problem, probably a page and a half or 2 of writing that you would do. And you would start probably by looking at shapes. Here's going to be a comparison between the box plots. And you would look at, if you took the box plots, you would say, well, the shapes of these two distributions, the Chiefs and the Niners, appear similar in the fact that their mins and maxes are close, their medians are similar, their quartiles are similar. And then you would throw in numbers. Because the median for the Chiefs is 227, the median for the Niners is 230. Being off by 3 pounds when you're talking about the number of people we're dealing with, that's not a very big difference. They have the same maximum value of 332, and their minimums are 170 and 178. Again, their shapes are very similar. They're somewhat symmetric. The median is a little bit low in both of their boxes. And that would be centers. You would need to decide, do I use the median or do I use the mean? Typically with a box plot, use the medians because that's what they give you. Median of 227, median of 230. Actually citing those numbers so I know that you know where those numbers are coming from. They're about the same. I mean, yes, the Niners is a little bit more, so they're a little bit fattier. I don't know. Thicker. A higher density of muscle mass because muscle's heavier than fat. How about that? They're more muscular. Pick what. Defend it.
I wouldn't say that.
I know that. All right. So the Niners are cream puffs, and the Chiefs. Oh wait, no, I'm talking. Sorry, now my politics are getting into it. All right, but anyways, looking at the centers, how do the centers compare? Having numbers that go with it. The average weight for the Niners was 242. The average weight for the Chiefs was 239. The means and the median for the Chiefs is lower than the mean and median for the Niners. But again, only by a couple pounds, so it's really not that big of a difference. IQR compared to IQR, you can see in the boxes that the IQR of the Niners is going to be larger than that of the Chiefs. And then you would show the numbers. You'd actually subtract this from that. Q1 from Q3, Q1 from Q3. You do those subtractions and compare them and say, we can see that the middle 50% of the 49ers weights have a larger variability than the middle 50% of the Chiefs, which means that the Chiefs' middle 50%, they're more similar because it's a narrower box than the middle 50% of the Niners, which is a wider box. That's what a wider box means. A wider box means there's more variability in that middle 50%. A narrower box means those middle 50%, you put them all together, their weights don't vary by as much as the Niners do. All right. So, and the shape, center, spread, and then outliers. You would do the calculation for one or the other, all right, or both. I mean, you can show the calculation. What I mean by that is show the calculations for one that you know how to do it. Q3 minus Q1 times 1.5, and then I go Q3 plus that, and it'll be somewhere up here. Q1 minus that, it'll be somewhere down here. Since all of the data falls within those two boundaries, there are no potential outliers. Same procedure here, upper bound, lower bound. So if you show the process for calculations once, that would be sufficient. You would not have to show it for the second one. But then you would just say, and the upper bound here is, and the lower bound is there. And you'll see that from both of these, there are no potential outliers. A great add-in question for me to ask would be, what if they pick up someone, I don't know who you'd pick up right before a Super Bowl to come play on your team that weighs like 110 pounds? Probably no one. But you put them on your roster because, I don't know, I don't know what you're doing. But then you have to decide, would that be enough to make it an outlier, that kind of thing? Or just understanding that you'd have to be significantly and sizably greater in mass to be an outlier when your Q3 is 280. All right, so 25% of your team weighs over 280. All right, 75%. All right. Second quartile, or Q1 rather, is 204. 25% of your team weighs less than 204 pounds. 75% of your team weighs more. All right. So, who's he play for again? The Chiefs. How many Chiefs are there? 75. Are they approximately normally distributed? Not well. They're actually bimodal pretty easily. There's a mode here, and then there's a mode here. We briefly touched on this a while ago. This is obviously not one of the highest points, but if I were to take and trace this curve, it mounds, comes down, and mounds again. If there's two pronounced top points, it's called bimodal, even though this one is not nearly as tall as that one. Interestingly enough, so are the Chiefs and the Niners. They're both bimodal, if I were to do that smooth curve on those. All right. So not normally distributed, not Gaussian, so the empirical rule wouldn't make sense. Recall, when we do all kinds of comparing, we do shape, center, spread, and outliers. So here's what would happen on an exam type question. In comparing shapes, we discussion on shape. Center, spread, putting in all those things, shape, center, spread, outliers, and calculations go in there. If you are essentially correct, so how I score things is like this on any given question, and it could be the entire question if it's a small question, or if it's broken up into parts A, B, C, and D, it's probably going to be 4 points per. Words here, essential, or essentially. If you're essentially correct, that's a 4. On a GPA scale, that's a 4.0, that's an A. If you are 3, that's what's called substantial. All right, and that would be equivalent to getting a B on that part of that question. If this is 2, it's called developing. So developing means you have right ideas and you've started, you just didn't execute. All right, that's a C, that's average. You've got a developing answer, you know how to kind of go about it. 1, that's minimal. That means I've shown up to class, I've heard these words, I'm using them the right way. I'm starting something that's probably not the right process, but I'm using the right words and terminology. I'm not wrong. That would get you like a 1. Now, if you start with something that's developing and then you make just an egregious mistake, like we're doing this, we're doing something with the weights, and then you start talking about them being categorical data, that's clearly you're not getting what's going on. Or you're developing here and you're starting with we got a histogram, but then you talk about using a pie chart to also support your work, also would be very wrong because you can't do those two. That could move you from a 2 back down to a 1. All right. if you are the type of student who in the past has tried to write down everything they know in the hopes that something will stick. And if you have what are called, I call them parallel solutions, where you're working on it and then you decide to do it maybe a different way, and then you're hoping one of those two ways is the right way, I grade the lesser right answer. So if the lesser right answer is a 1, but you did it the other way and you got a 4, you will earn a 1 on the question. It's my way of getting you out of that habit of trying to just vomit everything onto a page and hope that something sticks. All right? So that's procedurally how it goes. And then every question, as I grade it, and you'll see when we look at it later, I'll have it worth 4, if it's 4s and 3s and 2s and 1s, whatever. If there's 10 questions on the exam, that means it's out of 40 points because there's 10 questions each worth 40. But that doesn't mean, so if you get 30, let's say you had 3s on all of them, you would look at that and say 30 out of 40, that's a 75%. No, that's a B, that's an 85%. I have a calculation that I do that equates that in there. So people see sometimes if they come in and look at their test with me, they're, but how does that number compare to that number? I explain it all, and then they usually say, I don't understand what you're doing. Just go with me. If there's 10 questions and you get 30 points, that means you had an 85%. That's how it works. Back to this. So, while we're at it, then I got into just the habit of saying, well, let's do a couple quick other review type questions. So this guy, number 76 for Kansas City, weighs 308 pounds. Oh, we're going to do. All right. There are 75 people on the Kansas City Chiefs team. If 10 other players weigh more than him, what is his relative position? This requires you to remember, what does that mean when I say relative position? Relative position means? Pardon?
Offensive line.
Nope. Relative position means? Percentile rank. All right. So this gets in the, again, what I'm trying to emphasize here is there's a terminology in statistics. If I just say percentile rank, you'll go, oh, percentile rank, I calculate that. But relative position, relative to the whole, relative to all of them, where is he? So if he has 10 players who weigh more than him, he is position number, or he is ranked 65th. But that's not a percentile. He's the 65th person because there's 75 total, 10 or more than him. He's the 65th person, but relative to the number of teammates, he is 65 out of 75. And then for this case, relative positioning, here's where then you would convert it right into a percentile. And he would say that he is the, someone already calculated for me? 86th percentile. All right. In interpreting that, 86th percentile means 86% of his teammates are at or below his weight. 86% of those teammates weigh less than he does. All right? And then, if the distribution of weights of the Niners is approximately bell-shaped, Gaussian, what is the interval that would contain 95% of the weights of the players? This is recalling, oh wait, bell-shaped, Gaussian, that's like this. Mean is here. 95%. We make a normal curve with 3 hashes each way. That was this, the empirical rule. Mu plus 2 sigma. Mu minus 2 sigma. So I take the mean, 242.35. I would add 2 times the standard deviation right there, 46.34. I'd do it actually plus and minus, and I'd find 2 numbers, and I'd say, about 95% of the 49ers have weights between these 2 values. That'll do it for today.